Hey guys, I am Gautam from IIT Kharagpur and welcome to GChemix. In this video, I am going to talk about the NMR spectroscopy. And basically in this video, I will be discussing the what is NMR, the definition of NMR, then the types of NMR spectroscopy, then the theory behind the NMR spectroscopy, then one important point about positional motion, then origin of the NMR spectrum and different point regarding this, then population densities in the nuclear spin states, and NMR phenomenon shown by different systems, which systems show NMR spectroscopy and which doesn't, and of course the last point, that is the solvent, different kind of solvents used in the NMR spectrum. Okay, to get NMR spectrum. Okay, so what is NMR actually? So basic definition about NMR, the nuclear magnetic resonance spectroscopy, the full form of NMR spectroscopy. Okay, so NMR spectroscopy that actually involves the change of spin state, change of spin state. So just remember this point, change of spin state is the key point in case of NMR spectroscopy, to get NMR spectroscopy. Okay, so when this change of spin states occur, so NMR spectroscopy is the change of spin state, as I have told already. So this spin state changing of a nuclear magnetic moment occurs. Nuclear magnetic moment means it's a nucleus which has the charge and mass that will show the nuclear magnetic moment. Okay, I am coming at this point. Okay, so when any nucleus, basically some particular nucleus shows the NMR spectroscopy, but say any nucleus that absorbs electromagnetic radiation in the radio frequency region. This point is very important because they may ask question on which frequency is used in case of NMR spectrum. The radio frequency region spectrum. Okay, this is broad wavelength, this has a, and of course this energy, this frequency of radiation is used in case of NMR spectrum. And also one is radio frequency region radiation, electromagnetic radiation is applied in systems, and another is you have to apply strong magnetic field on that particular system. So what happens if we apply both of these? I will be discussing it a little bit later. Okay, so first let me tell about the types of NMR spectrum. So there are two types of NMR spectrum. First, 1H NMR, that is also called PMR, that means proton NMR spectroscopy. Another is 13C NMR, that is called 13C NMR, of course, spectroscopy. Okay, so basically some other NMRs are present, for example fluorine, then phosphorus, etc. But basically in this video I will be discussing the 1H NMR or PMR spectroscopy. Okay, so why we need to learn this PMR spectroscopy, why and how PMR spectroscopy helps us. So actually PMR spectroscopy along with the IR spectroscopy, IR data, helps to determine the actual structure of an unknown compound, basically unknown organic compound or unknown inorganic molecule. Okay, that was the essence of the NMR spectrum. Okay, so now coming to the theory of NMR spectroscopy, especially PMR spectroscopy. So let's talk about first about the nuclear spin. So what is nuclear spin? Nuclear spin means, so I will tell you in very easy words. You know the rotation of the earth, about the rotation of the earth, how it rotates in its own axis. Okay, so its rotation will be like this. So every proton rotates like this, like Earth's rotation. Okay, so this rotation creates as proton, that is positively charged species, and any charged species that rotates creates a magnetic field, creates its own magnetic field, and here in this direction. Okay, so if it rotates and creates its own magnetic field or own magnetic field vector, then that vector quantity is called magnetic moment. Okay, magnetic moment, this is the definition. So when a charged species rotates, that will create the magnetic moment. Okay, so these nuclei that is acts like a bar magnet. Okay, so bar magnet means there will be a north pole and there will be a south pole. So it looks like this. So why I am comparing it with a bar magnet, I will be discussing a little bit later. Okay, so here one more thing is important, that we have to consider one point about spin quantum number. So spin quantum number is very important to understand the NMR spectroscopy, the theory of NMR spectroscopy. So what is spin quantum number? So number of allowed spin state are also here quantized. Quantized means at a particular value of spin quantum number, the NMR data, NMR spectrum can be shown. Okay, so let's take the spin quantum number I. So there will be only 2i plus 1. So you may compare this like this. You know about the azimuthal quantum number, that is L, magnetic quantum number, that is M, and M have the value total 2L plus 1, that is minus L2 plus L. Okay, so here also 2i plus 1 number of spin quantum number or allowed spin states will be present. That will show the of course NMR spectrum, that magnetic moment will show the NMR spectrum. Okay, so here 2i plus 1 number of total possible spin states are present, and that is minus I2, of course plus I, like the similar one. Okay, of course the difference will be 1. Okay, and now let's take an example, that is for proton, say I, that is value, that has value half. So there will be total 2i plus 1. So if we put I equals to half, we will get 2, that is 2 spin states, possible spin states that are allowed are possible. So what are they? One will be minus up, one will be minus up, and another will be with the difference of 1 will be plus up. So minus up and plus up, these two possible spin states are present in this case of proton. So I will be discussing much more example in the last of this video. Okay, so just keep watching. So next, coming to another point, that is about the effect of external magnetic field. So what is the effect of external magnetic field, and what external magnetic field do in this system? Okay, so let's take an atom which has the positional motion, or which the system which rotates like the earth. Okay, so in case of that system, here the system is a proton. Okay, so in the absence of any magnetic field, okay, so nucleus, all the nuclear states are degenerate. So nuclear states means as I already gave you the example, hydrogen, which has I equals to half. Okay, so there will be total 2 spin states, minus up and plus up. So these 2 spin states will be degenerate. Okay, and what is degenerate, what is non-degenerate, I am coming to this. Okay, so all the spin states will be degenerate. Degenerate means minus up and plus up will be equal energetic. Okay, and the populations of each spin states are equal. Population means in each spin states there will be equal number of possibility, or equal number of nucleus in each spin states. Okay, and thus all the orientation of the nucleus will be same, and thus all the orientation of the nucleus will be in random manner. Random manner, say it's up spin, it's down spin. Okay, up spin means it rotates like this direction, or the nucleus rotates like this direction. Okay, so if this direction is up spin and this is down spin, so in case of in the absence of any externally applied magnetic field, the rotation is random, so it may rotate in any of this direction. But in case if we apply the external magnetic field, then what will happen? Then this nucleus, only two things can happen. One, suppose the externally applied magnetic field is towards like this, say magnetic field distance is B, and two things may happen, that is it may align, it means the all systems, okay, all the nucleus, it may align with the externally applied magnetic field, or it may not align with the externally applied magnetic field. If it aligns, then we will say the spin state is plus up and is represented by alpha, and if it doesn't, then we will represent it minus up and beta. So it is beta spin state, this is alpha spin state, and alpha spin state is much more stable than beta because it aligns with the system and it doesn't. Okay, and because of this, the beta spin state will be higher energy because it's not stable, because it is not aligning with the externally applied magnetic field, but it's aligning. So that is why it is stable, it is unstable. So unstable system has higher energy. So if we consider energy diagram, then this will be beta, this will be alpha. Okay, so alpha more stable than beta. Okay, so what is happening here is that when we apply any kind of magnetic field, externally applied magnetic field, this kind of spin states, the degeneracy is loosened. Okay, and finally we will get this kind of two states, alpha and beta spin states. So let's discuss this by bar magnet. So it is, say, north pole, this is south pole of a system. This is also north pole, this is south pole. Say this is the externally applied magnetic field. So if a bar magnet is like this, so it will align when this will be south pole, this will be north pole, because attraction present. But if it align like this is here north, this is here south. So north repulsion, south repulsion. That may cause the increment of this energy, increment of the energy of the system. Okay, and that is why this will be like beta and this will be like alpha. More stable, less stable, that is higher energetic. Okay, so this is the significance of the bar magnet. Now coming to another point, that is about positional motion. Okay, so what is positional motion? So positional motion is basically nothing but the motion of the nucleus. Okay, nucleus means the spinning bar magnet or the spinning magnet. You can consider nucleus as a spinning magnet. Okay, so how nucleus actually rotates? That will be the rotation of the system, and that is called the positional motion. Okay, so the top, or you may say the top, or it's called Hindi or Bengali, it's Lattu or Latim. Yeah, I hope you know, or however. So it's called a top, or you can consider the rotation of the earth. So it will rotate like this. Okay, so it's this direction or this direction. Okay, so this rotation is called the positional motion. Positional motion is important because of the rotation, maybe upspin, downspin, means the rotation of the nucleus towards this way or towards this way, as I have already seen you. Okay, this is called the positional motion, the rotation of the nucleus. Okay, so now coming to next important point, that is about the origin of NMR spectrum. So this is very important. Origin, how NMR spectra originates. Okay, so this will be, what will be the origin? So origin means, say a nucleus or a set of nucleus are in alpha spin state. So 4 nucleus. Okay, when we apply the external magnetic field, and that is B strength, and H nu, that is the frequency of the radio frequency region. Okay, this is the energy. So energy you are applying, and also externally applied magnetic field is present. So what will happen? Alpha spin state and beta spin state. Alpha spin state will be converted to beta spin state. Say 3 spin states are same, but 1 spin state changes. Okay, so these 3 are in alpha as well as previous one, but these changes to beta spin states, and this changing is the key factor of showing the NMR spectrum. Okay, so this energy difference shows the NMR spectrum. This is the basis of the NMR spectrum. Okay, so when we apply the magnetic field and along with the radio frequency region energy, this kind of spin flipping occurs, and that gives us the NMR spectrum. Okay, this is the basis. And now we are considering why. You may ask why alpha to beta spin state flipping is possible, because say this is alpha, this is beta spin state. Okay, so this is the energy level diagram. So when this is, of course, aligned with the magnetic field, this doesn't align with the magnetic field, beta spin state. So this energy gap, that is called delta E. Of course, from Planck's law, delta E equals to H nu. Okay, so this energy gap should be very, very less, so that at room temperature, at around room temperature, alpha spin state to beta spin state spinning conversion occurs. So here it is alpha, this is aligned with the applied magnetic field, but here it doesn't. So energy gap should be less, so that nucleus can jump from this state to this state. Okay, so this should be the condition. The energy gap should be very, very less. Okay, so this energy gap, I want to add something, because from this energy gap you may face questions in JAM or NET or different other examinations. Okay, because here is one important thing. Just let me clear the board first. It will take some time. But why this kind of rotation, this kind of flipping occurs? because of this externally applied magnetic field and the radiation which we are applying. Okay, so now coming to this frequency. So just remember, one thing you have to remember, that the frequency of radiation, that is the radio frequency, okay, which is equal to the precessional frequency. Of course, if we apply any say this is the nucleus, if we apply the frequency, so it will rotate in this direction or in this direction. Okay, so this rotation is dependent on the precessional frequency which we are applying from the outside as radio frequency. Okay, so precessional frequency is directly proportional to the strength. So if we apply the strength, more strength magnetic field, that is B, then the precessional frequency of course increases, and thus we will get that the nu, that is precessional frequency, is proportional to B. Okay, this is the first formula. So next, the energy difference. I have already shown that alpha beta energy state, that is delta E. So this energy state, this energy delta E, energy difference, of course the function of the externally applied magnetic field, because if we apply more magnetic field, then energy difference will be greater because splitting occurs here. Okay, so delta E is a function of B. Okay, and the magnitude of the energy level separation, this magnitude, that is delta E, of course, also depends on the particular nucleus involved here. Okay, because for every nucleus, for hydrogen, for chlorine, for other nucleus, each nucleus has a different ratio of magnetic moment. Okay, to angular momentum ratio. So magnetic moment and angular momentum ratio, magnetic moment by angular momentum, this is called gyrometric ratio. Okay, or gyroscopic ratio or magnetogyric ratio in the case of when we are applying external magnetic field. Okay, so magnetic moment of the particular system, maybe hydrogen, maybe chlorine, okay, anything. So here we are considering hydrogen, so consider only hydrogen. So magnetic moment when it's rotating when it's shows precessional motion, then the magnetic moment is creating by this system, and the angular momentum also created. Okay, so that is the ratio. This ratio is called magnetogyric ratio. Okay, so this ratio is very, very important. You just need to remember this ratio. You may face question from this formula. Okay, just note down these ones. Okay, so let's move on. And this is actually a constant. Okay, so this difference, so this energy difference delta E is of course dependence of course on this. So remember, this is a function of, already it was B, and one is adding, that is of course, sorry, this will be magnetogyric ratio and of course B. Okay, so this ratio, and delta E, you know from Planck's equation, is delta E equals to h nu. Okay, so you of course know that the angular momentum, okay, is quantized with the unit of h by 2 pi from Bohr's theory. Okay, so just put here as h by 2 pi, and finally we will get this one, magnetogyric ratio h by 2 pi, and of course magnetic field, which will be equals to h nu. So this will be the required formula. So this formula is very, very important, where nu is the frequency of the energy of the radio frequency region. Okay, and this is called the magnetogyric ratio. It may call gamma. Okay, so if this kind of rotation possible clockwise, then we may say gamma is greater than 0, and this kind of rotation is possible, then we may say gamma less than 0. Okay, so just remember this formula and this formula. You may face questions from this one or this one, because I know one question came from this formula in JAM, maybe 1 or 2 years before. Okay, so now coming to another point, that is the population densities of nuclear spin states. So what is population states? So population states comes when a system shows different kind of spin state flipping. Okay, so say it is in the alpha spin state and it is also in the beta spin state. So during conversion, okay, this kind of population of spin states are possible. So what is this? So say this is energy diagram, delta E or E. This is alpha, this is beta. So I have already said you that this electron flipping from alpha to beta spin state is possible because the energy gap less. So if as the energy gap is very less, so this kind of spin states flipping is possible. So this is called, so say here NUP, that is upper, it's upper, this is lower. N upper number of spin states are present right here, and here N lower spin states are possible. So what will be the required formula to get this? N upper by N lower. So it will be actually the statistical mechanics formula, which will give us that this value will be equal to the e to the power minus delta E by kT, and you know about delta E, which is e to the power minus h nu by kT. Nu is the frequency of the radiation which we are applying. So k is the Boltzmann constant right here. So if nu, the frequency, is 60 mHz, the applied frequency, so N upper by N lower, I have already done the calculation. So N upper by N lower will be 0.99991, which will be equals to 1000009 by 1000000. So you can see that in N lower spin state 9 nucleus are present more than the upper state. Okay, this is because of because in alpha state there is less energy and it's stable, so the systems try to stay in the stable state. Okay, but the difference is very less. That means this energy gap, of course, very less. Okay, that means at room temperature you can easily give energy to the system, and it will convert its spin state from alpha to beta. Okay, easily at room temperature. So this is the significance of showing the population densities. Okay, so because of the energy gap is less at room temperature. Okay, so when here one question comes, that when alpha to beta spin states, suppose alpha to beta spin states conversion isn't possible, then you will not get any kind of signal in the NMR spectroscopy. That is called saturation of the signal. So that is called saturation of the signal. Saturation, this point is important. Saturation of signal. Signal means in the NMR spectroscopic machine. Okay, so now coming to next topic, next important point, that is about the nuclei that exhibit the NMR phenomenon. So which nucleus will show the NMR spectroscopy, which will not? So that is a question you can face in your mind. Okay, but that is actually very easy. You may say I will provide you a table that will help you a lot in answering this type of questions. Okay, so what will be the system? What will be the formula? What will be the formula? How to determine which systems will show the NMR phenomenon, which will not? So that is, I am considering a table that is, here it is mass number, here it is atomic number, and finally here it is spin quantum number. Okay, so if mass number is odd, atomic number is odd or even, okay, and then spin quantum number will be positive, that is maybe half, 3/2, 5/2, etc. If mass number is even, this is also even, then it will be 0. And if mass number is even, atomic number is odd, that will have 1, 2, 3, any value. Okay, so just consider one thing, that if spin quantum number, that is represented by I, if I is greater than 0, then the system will show the NMR spectroscopy, NMR spectra. Okay, so I should be greater than 0. So that is why, if say let's say an example 13C6. Okay, so it is odd, that is odd, mass number odd, atomic number is 6, that is even, that will show this kind of spin states, spin quantum number, and that will show the, as it is spin quantum numbers are positive, so it will show the NMR spectroscopy. Let's take another example, 10B5, boron, its compound. So here 10, that is even, 5 is odd, so it will show positive spin quantum number, that will show also, of course, the NMR spectroscopy. Okay, so this system will also show the NMR spectroscopy. And the last example I want to give you, that the 12C 6. So 12 C6, that is 12, that is even, 6, even, atomic number even, and C, we are considering C, that is spin quantum number as 0, so the condition is not fulfilled. That is why the system will not show any kind of NMR spectroscopy. Okay, so this is all about the different kind of system which will show whether it will show the NMR spectroscopy or not. Okay, so now coming to last point, last very important point of this video, because I will make another video, maybe 2 or 3 videos to complete whole the syllabus for NMR spectroscopy, and you will get all this in between 2 or 3 days. Okay, because JAM exam is coming and I just want to help you to figure out all these questions, okay, in JAM examination from NMR spectroscopy, and I will give you also example in the subsequent video. Okay, so just keep watching. So now coming to another important point, that is what are the solvents used in NMR spectroscopy. So you cannot take a solid sample to do NMR spectroscopy, so you just have to liquefy it. Okay, so you have to take a reference sample, and that reference solvent will be in most of the cases used in the NMR spectroscopy. The most of the cases the solvent used is the CdCl3, that is deuteriochloroform. Okay, and it is because that the most organic compounds are soluble in CdCl3 because of this solubility. Okay, and that is also soluble in CsCl3. So as we are considering proton PMR, so we cannot use hydrogen atom. So here we are using the deuterium atom. Okay, so that is why it is CdCl3. Okay, so some others of course solvents are present, that are actually varies when you are considering different kind of systems. So for acidic medium, we just need to acidic sample. We just need to soluble that sample in CCl4, tetrachloride, or carbon tetrachloride. Okay, so CCl4 is used for acidic compounds or acid sensitive compounds. Okay, next is Dmso. Dmso is used for non-volatile compound, or if you want to do if you want to get the NMR spectroscopy at high temperature, very high temperature, that is maybe 140 degrees Celsius, okay, then you may use Dmso. Okay, then coming to C6D6, it is not normally used, but it is often used with addition of the CdCl3. So CdCl3 and CdA6 is actually added with the CdCl3. Okay, but it is not a common reagent. Okay, normally it is not used. Then coming to CD3 whole twice CO. Okay, this is called hexadeutyl acetone. It is also used for routine NMR spectroscopy. Routine NMR spectroscopy means regular spectroscopy. Okay, so next coming, that is not that much important. Last is CF3 COOH. So this is actually the trifluoroacetic acid. So this is actually used for important. Just consider, just note down that amine for amino compounds and heterocyclic compounds. For amine and heterocyclic compounds, this solvent is used. Okay, so this is all about the whole things. The solvent used, then the which systems show the NMR spectroscopy or not, the basic idea, basic theory, how NMR spectroscopy is, which system shows, and the basic idea about that. Everything I have already discussed. So if you have any question, you can ask me in the comment section, or you can join my Facebook group. You can get the link in the description of that Facebook link, and of course you can check my blog to buy books on NMR spectroscopy. That will be very helpful, because NMR spectroscopy is necessary for your whatever BSc, MSc, Masters, PhD, postdoc, everywhere. So just you should have the clear concept on this. Okay, so if you want to buy book, then you can go to my blog, and you will get the link in the description below, and buy from there. Then that will help me a lot, because that will provide me some kind of commissions if you buy the books from my link. Okay, so whatever you want, if you want to buy, then try to buy from that link, otherwise you can ignore this. So whatever in the next video, actually this is not over actually, because in the next video you will get next topic, next important series. Actually it's a series, so you will get the next topics. For example, in the next video I will be discussing actually chemical shift, about chemical shift. Okay, so that is very, very important. Okay, so you may get the video tonight or tomorrow morning actually. Okay, so just keep following, keep watching, and thanks for watching.